I will talk about depth and normal fusion, which is for improved 3D reconstruction, which is basically the topic of the previous talk as well, kind of a data fusion from different modalities. And we are tackling it by a variational approach in this particular paper. Good, so let me jump in directly into the formula we are trying to solve here. Basically, with many methods we have heard about here at this forum, or we know from state of the art, we obtain on one hand side often a coarse depth model by different means. In our case, it is light field, or we can say in general multi-view stereo approaches. We know that these are usually very good in absolute sense, so you get good, depth accuracy in absolute numbers, but it usually suffers from depth detail. So on a plus side of these methods, one can say you get good absolute depth but low depth detail. On the other hand side, there are methods like photometric stereo, which can deliver, so to say, surface normals, but it may not be just surface normals. I mean, if we think more general, these methods are very good in local details, in fine 3D or 2.5D structure, but they are not very good usually in absolute depth. So the depth, we can say, is at most relative. Maybe some of you try to do a 3D reconstruction out of the surface normals, which are subject to noise. Usually these reconstructions don't look good. Especially, they don't usually preserve depth discontinuities, and that's typical trouble with these methods, I mean, apart from the others. And our goal in this research, in Doris's thesis, was to come up with a method which can efficiently fuse these two, but it can also be generalized for more modalities, more depth modalities, in order to obtain very good, high quality, highly resolved depth model, which both benefit from absolute depth of one, let's say, sensor system and good relative depth sensitivity of another sensor system. In this work, we will talk about light fields and photometric stereo in particular. Good, so let me talk now about what are the principles, typical principles of acquiring light fields, and later on also photometric stereo. So if I say light field, I mean in general multi-view stereo, but light field has a nice property that it's nicely structured, and there are very nice and powerful algorithms which can be applied if one has a regularized, well-structured, calibrated light field. Usually light fields are acquired with some sort of camera array. It can be either a real camera array, which consists of multiple cameras, which are, put together in a certain structure. But usually these systems are error-prone, and the complexity of data capture, grows with the number of cameras. So, like, synchronization issues are usually a problem. So nowadays there are also on the market a couple of light field cameras which use one sensor and micro-lens arrays which are put in front of the camera or in front of the sensor in order to get this angular separation. So what the light field camera delivers in the end, I hope you can see the video. Basically you get a sequence or set of images of the same object from multiple directions. In ideal case, you know exactly these directions. So you know where your cameras are. Of course, if you don't know, then there is something which is called unstructured light fields, or it may be also be linked with structure from motion principles. If one is in luck and the camera system delivers a nice and structured light field, then there is a whole set of methods which basically fit into something which is called epipolar plane image analysis. And that means that the depth can be derived from an angle of certain structures in these light field stacks. I'm not going into detail here, but basically one can apply, matching, which we do, but one can also apply different approaches like structure tensor approach, which can also deliver very similar property and can be used for depth estimation efficiently in the light field domain. I hope you can see it here at this image. If not, then please look into your handouts. Usually what comes out of these methods is a depth model, which is nice and good, but it lacks details, right? On the other hand side, there is photometric stereo. Typically, photometric stereo is acquired with a light dome or some sort of segmented ring light devices. The difference is here we have just one single viewpoint, one single camera, and we are instead using multiple light sources to separate between different illumination directions. And from those different reflection responses, we can derive surface orientation, local surface orientation, and we call it surface normal. And from these normals, these normals contain usually a vast amount of local 3D information. It can be directly used very nicely for, I don't know, some local assessment of errors like scratches, those which do not really have like significant depth. But if we are still interested in a depth absolute depth information, we would need to integrate the profile or the surface, the depth model. And well, here we are attempting to complete this structure or this scheme by combining these two modalities and get finally a good high-quality depth model which contains both absolute depth and good local detail. Good. Why are we at all interested in this? At AIT, we have over a couple of years developed a technology which we called inline computational imaging, which is a technology which basically combines line scanning and light field imaging. We came up with a camera system which is illustrated here on this sketch, where we employ a multi-line scan sensor, which is an area scan sensor where we can define a subset of lines which are sparsely taken from the sensor. And these lines, you know, over the time, the object is moving in front of our camera on some sort of conveyor belt or linear stage, as we know from production lines. This system is designed for production lines and for different inline inspection scenarios. And over the time, we obtained from this system with a single camera, single sensor, and single lens, which is, of course, a huge advantage for our customers, that what needs to be maintained is just a single camera system and calibrated as well. That's very important. We obtain multiple images of the same scene, and these multiple images you can hopefully see here on this illustrative example. It's a coin acquired by our inline computational imaging system, which is seen, you know, in these multiple views from slightly different directions. Hopefully you see the movement from left to right in the foreground and from, let's say, right to left in the background. Hopefully you can see that. But that's not everything. Probably you see around the edges that there is, you know, something going on with the intensities, and these are photometric effects, which we, at the start of our research a couple of years ago, we thought that they are actually not good. They are actually making problems for our matching algorithms and so on, because the matching is considerably harder under such conditions. But actually those are photometric effects which we in the end used for, or are using currently for, estimating surface normals. So actually it's not an inconvenience in the end, it's an extra information we can use from the same data set. And this information comes from the fact that there are, as usual, two light sources, line light sources. They are slightly diffused to illuminate not just a single line, but more, usually larger area. And these two light sources have, strictly speaking, slightly different configuration with respect to each view. And that, given a correct calibration, can be used to extract surface normals and proceeding with our fusion I will present later. in the next slides. So what we get from our system is a simultaneous capture of light field and photometric stereo. That's why we are interested in this fusion. Good, so now let me briefly explain what the variational approach to solving such a problem actually means. We have this basic formula, which you see on a slide, where we have a data term, depth data term. We measure depth from our low-resolution depth camera. We measure surface normals, that's d hat. We measure surface normals from our light dome or photometric stereo, that's n hat. And we want to find a solution which is close enough to our measured depth, which is close enough to our measured normals, and at the same time we can also plug in a regularizer, which is going to be shown as very beneficial in the end, in order to get, like, fight the noise, for example, a bit better. Yes, so now let me proceed. This is one of the more complicated slides. So basically what is usually done in the state of the art, the depth data term is considered to be a quadratic data term. So there is d hat and z, they should be quadratically close to each other. So there is quadratic penalty on the deviation from d hat. That's typically in the state of the art, and in the end of the day we remained with this. We didn't touch this part of the problem. And then when we scanned, when we searched state of the art, we detected, we observed that there are basically 3 different approaches, apart from the others. There are plenty, but these are very dominant ones. Firstly, the most simple one is a gradient-based method. So from, if we want to remain in a scope of linear least squares, you know, if we want to solve this problem quickly, and that's why we do not want to have a complicated error term or energy term, linear least squares there are very good solvers for that. The gradient method comes very handy. And the gradient-based method says that if I make a gradient of my solution and just take a difference from the measured gradients and which are derived from normals and penalized by a square of this distance, that should lead to a good solution. This penalty, here is a peculiar graph. This penalty, which is created by such a photometric penalty function, can be visualized in this form. That means that if we have a local surface detail with a certain orientation, let's say it's flat, which means it has a 0 degree inclination angle, and my solution deviates from this by a certain deviation angle, such an energy function gives me very different penalties dependent on the solution. That is quite counterintuitive, and it actually causes certain artifacts in the final solution. What you can see here is that such a formula is tolerant if the ground truth orientation is flat, and is very, very strict if we are operating around edges. Well, here a result of such a method. This is a synthetic data set from Stanford, Buddha. Here is a simulated coarse depth model, and this is an improvement with a gradient-based method over such a simulated depth by a gradient-based method. What one can see, I'm not going into detail, one can see that it causes certain blurring. For example, here in this, hole here, there is a lot of blurring visible. Then there is another method, which is projection method. It was published in 2005, and this method is way better, I can tell you. It is still linear least squares, it's way better, but it still causes a lot of blurring. It's still visible. It's way better compared to gradient-based method regarding the noise. If there are artifacts or very strong noise present in in the normals, then gradient-based method would fail entirely, but the projection-based method would work still. Then there is normal scaling method proposed by Heber in 2015. And this method, according to the penalty function, looks quite similar, but we have proven or shown that actually it is operating somewhere in between the gradient-based method and the projection-based method. Good. Now to our approaches, we have generalized over the projection method by adding, local weighting and some, exponent which we've optimized, and we found that there is some magic number which works nice, but it's good, or sometimes this model might be beneficial because it is powerful, it delivers significantly better results, but it's still within the linear least square domain, which means it can be solved very efficiently and quickly. Here is the result, and the next and the final method I would like to touch upon is the total generalized variation method, where we have used this regularizer, which is a very clever one, because it assumes something about the solution, how it should look like. This penalty actually enforces the solution to be piecewise linear with discontinuities, and that's very, very nice about it. Good, and these are the results. I hope you can see some improvement, especially here in the hole. I try to find the location where some differences are visible. I will show you also some numerical numbers now. Results. Here we have better quality around the steep edges. Good. Now a few more results from a synthetic data. Qualitatively, it looks that the TGV method, the final one, R2, ranked better or looked better. The solution looked better than the state of the art, but the TGV method looked the best according to our observations. Now, some numerical results. There are plenty of numbers and comparisons with it, but these are the overall plots. The reference, initial normals and initial depth model, very bad. With the state of the art, it's better, and with our two approaches, it's again better than the state of the art. And our TGV approach, which we use in our current technology, is ranked among the best in all our testing cases. Good. Now some real examples. Here we have, again, gradient-based method for the reference, then the projection method, and then our two proposed methods. And again, the TGV method delivered the best result. You can see that the edges are not blurred. All the other methods, including our proposed one, are generating blur around steep edges, discontinuities, while the TGV method did not. Another example from real domain, and this brings me, I will probably skip over use cases of our, or maybe just briefly, we have for our inline computational imaging, which includes also the algorithms I have presented to you. We have plenty of industrial applications. It's very flexible and very, I would say, universal method. And it goes from industrial inspection through electronic parts, metal parts, print inspection, and so on. And it leads me to the conclusions. As for the methodology, variational formulation of this problem we find as a very handy and convenient one, because we have all the components under very good control compared to, for example, machine learning. One could solve the same problem by machine learning, but there we would be completely dependent on data, which is there in the training phase, while here we have our prior knowledge very clearly visible in the solution, and the algorithms seem to be actually the same, computationally same complex or easier than machine learning. So here you have an example where still traditional approaches may beat the machine learning approaches. We have plenty of real use cases for these methods, and an outlook would be local weighting from methods, different sensing methods. we have confidence information about where the measurement is reliable, where it is not. And in our variational framework, we can include this information very easily, and the solvers would work equally well. Some references, and thank you for your attention.